Okay, so let's resume and have the second part of Alberto's lecture.
So this business of localization has been carried out in many cases. In the past, in many topological field theory. And then on many manifold, the favorite one in different dimensions. Favorite ones are always spheres quotiented, product of spheres in 3 dimensions, Seifert manifold. The original case by Pestun was S4, and then there is the interesting case of S3 times S1, which is a superconformal index. People have studied here ellipsoid. And people have also studied higher dimensional field theory. Here also on Sasaki-Einstein. Manifold. The purpose of this kind of computation is various. In many cases, you can use this partition function to test dualities. The original computation allowed to compute vacuum expectation value of Wilson loop was done by Pestun. Then Kapustin, Willett, and Yakov studied 3-dimensional theory. They tested various types of dualities. In 5D, for example, a typical question is if the theory has a fixed point with some enhanced symmetry, the partition function should be able to capture that, and so on. So there are so many cases that I'm not going to review, and cannot even give the list of all the authors that works on these topics because it's too much. If you want to have an introduction to the techniques of localization, probably you can have a look at this good review by Marcos Marinho, which can be also useful as a background for ABJM that I will discuss in the last part of this lecture. Or there is this very big book. I haven't really looked at it, so I cannot guarantee that it is readable and every single chapter is readable, but essentially the editors are Zabzin and Pestun. It's divided in chapters, and they cover all this stuff in all different dimensions and different supersymmetries. Now, the case that I want to discuss, because it has an application to black hole, is the case of S2 times S1. To be more precise, I want to discuss a particular type of theory, which is topologically twisted, and define a partition function. The most general one that I can define in this method, with this method, is a partition function on a Riemann surface times a torus, and I will call this in general, and I'll explain why later, the topologically twisted index. It will be an index, so there will be some counting that I'll explain later, counting of BPS states. And this is a Riemann surface. D can be 0, 1, or 2. And for simplicity, I'll focus at the very beginning to the case where the Riemann surface is a sphere and there are 3 dimensions in total. You can find explicit details about this model in this paper. So here I will try to be to give you not too many technical details, but if you want to have a look at them, you can have a look at this paper, and there is also some interesting work by Clossec, Cremonese, and Kim last year, and a couple of papers by Clossec, Kim, and Willett. I put it in bracket because he is only in the second paper. Okay, so the setup for the example involves 3 dimensions. Why 3 dimensions? I can tell you, going ahead, the logic for the black hole counting problem. I will discuss tomorrow and Wednesday black holes which are asymptotic to ADS4, and so on the boundary there will be curve manifold, which in the Euclidean is precisely S2 times S1. So this kind of supersymmetry is precisely the supersymmetry that is realized when you want to express the microstate of the black hole as states in a quantum field theory. So that's the reason why I choose this particular example. The reason why this is the right choice will be clear tomorrow when I write the metric for the black hole for you. Today is just a quantum field theory example. And I want to consider n equal to 2 supersymmetry in 3 dimensions. There are 2 multiplet. The vector multiplet and the chiral multiplet, which contains the following fields. This is the vector multiplet, and this is the chiral multiplet. I hope that now I'm writing big enough. Look at the vector multiplet. This is essentially the dimensional reduction of the standard vector multiplet in 4 dimensions. It contains a vector, a fermion, and when you reduce from 4 dimensions to 3, you also get an extra scalar field from the compactify direction. So this is the 4th component of the gauge field, and there is an auxiliary field D. The chiral multiplet has precisely the same form as in 4D. There is a complex scalar, a fermion, and an auxiliary field. Here I am in 3 dimensions. So these spinors are all Dirac spinor in 3D. I also assume that there is some R-symmetry. So there is a symmetry rotating the gauginos. I choose to give a charge -1 to the gaugino. It's not the common one, but is the one for which I already have written the Lagrangian that I'll show you in a moment. Is on the other blackboard. So I was too lazy to change the convention. I agree that is not the standard one, but doesn't change anything, okay? So I choose charge -1 for the spinor. The scalar will transform with some with a phase times the R charge of the scalars, and the fermion will have R charge R phi -1. Okay, this is an R symmetry. The background is the following. The metric is the metric known as 2 times S1. So I write it for completeness. Is boring. Clearly, there is a sphere here. There is a radius of the sphere. There is t, which is Euclidean time, and there is a radius for the S1. And the other thing that I want to do, this was case A in my previous, was case 1, the covariantly constant spinor case in the discussion of the previous hour. I want to choose a background for the R symmetry. And the background that I choose is this one, on a sphere. So I put essentially a monopole, so I should write it better without the space-time index as a one form. This is the R symmetry. It's a monopole of minimal charge. And again, if you take a spinor, which in 3 dimensions is a 2-component object, I can choose the gamma matrices to be in the Euclidean, the 3 sigma matrices, and you assign charge -1 to epsilon under their symmetry. Then the equation that I wrote before for the covariantly constant spinor case, just read in this way. Now, very stupid exercise, compute the spin connection for a sphere. You certainly have done it many times in your life. It has the form of a monopole. And you see that the form of A has been chosen in such a way that it cancels this one. It's enough to choose a spinor which is an eigenstate of gamma 3. So essentially there is a component plus and the component minus is 0, because here you get gamma 1, 2, which is gamma 3 times an I. The I cancel the I, and the spin connection cancel the mu, precisely. So these two guys cancel. I'm twisting the theory by turning on a background for the asymmetry. Okay, so I can preserve supersymmetry in this stupid way. I take a constant spinor on my manifold. Epsilon will be independent of theta, phi, and t. And for the Lagrangian, let's see what I should do. For the Lagrangian, I can use one of the 2 methods I discussed before. Noether method is not too difficult. Here you can easily get. This is the Lagrangian. It's scary because it's on 3 lines, but it's not so different from the Lagrangian that you write in Lorenz's signature. So the first line is the gauge field, F mu nu square, covariant derivative of the scalar, the auxiliary field. This is the kinetic term for the fermion, and these are just Yukawa coupling. So it's not so different from the flat space Lagrangian. The second line is something that you can have in 3 dimensions. It's a Chern-Simons term. So here there is a coupling K, which is quantized, should be an integer. And this is just the supersymmetrization of the Chern-Simons term. Again, even the second line is very similar to what you write in flat space. Third line, if you have a chiral vector multiplet, well, you see that the terms that you write are the usual one, kinetic term, F square, and Yukawa couplings. No, there are a few additions with respect to flat space. For example, here, the curvature of the R symmetry enters explicitly here in this coupling. But for the rest, it's just a Lagrangian, okay? This is invariant under the transformation of supersymmetry that I wrote here. I will not use much those, but let me notice a few things. As I told you before, when you go to the Euclidean, you typically have to double fields. So fermions lambda and lambda dagger are to be considered as independent guy. So you see, for example, that the transformation Q annihilates one of the two, but not the other. And if lambda and lambda dagger are no more the complex conjugate of the other, also scalar field should not be considered as complex conjugate. So phi and phi dagger should be considered in general as independent fields. So everything is double, including the transformation of supersymmetry. So here I have an epsilon, and here I have an epsilon tilde. Both satisfy the equation that I wrote above, so these are just top component of a two-dimensional vector, but I have two independent ones, and so that I have two independent set of transformation. So the logic is that supersymmetry somehow is like having complex coordinates. Phi and phi dagger are like z and z bar, and the same happens for the fermions. Okay? So in a sense, this is a holomorphic transformation, and this is an anti-holomorphic type of transformation. And the other important thing for understanding the physics of this theory is sigma. This is general, it's not related to Lorentzian Euclidean compact space or other things. Sigma, which is the scalar field sitting in the vector multiplets, coupled to the matter field as a master. This is typically known in 3 dimensions as a real mass. For real mass, I mean a coupling of this type, which is supersymmetric. So this is the dynamical because sigma is a component of the vector field. So it gives mass to the scalar fields, and it gives mass also to the fermion, to the matter fermion. Okay? Now, the other important story is the following. Computation show that if I call the 3 terms in the Lagrangian with different name, the Yang-Mills Lagrangian, the Chern-Simons Lagrangian, and the matter Lagrangian, one can check that up to constants and coefficients, the Yang-Mills part of the Lagrangian is the supersymmetry transformation of something. Actually, it's QQ bar of something. This is a typical structure of all this computation. And the same happens for the matter Lagrangian. And the precise expression is up to coefficients is psi bar psi plus 2i psi bar sigma psi. So essentially, the Yang-Mills part and the matter part can be written as Q plus Q tilde of something. They are the Q of something. In the logic of localization, this is the guy that I called capital Q before in the previous lecture. And what I told you is that given a supersymmetric Lagrangian, you can always add the Q of something without changing the path integral. In this particular case, this means that since this guy here and these guys here are the Q of something, we can call it exact form, thinking of Q as sort of differential operator. So the Yang-Mills Lagrangian and the matter Lagrangian are Q exact, which means that the coefficient here, G and E, I put 2 different ones for Yang-Mills and matter fields, can be varied arbitrarily. In particular, you can send them to 0. So you can evaluate your path integral by sending the couplings to 0. The only term which is not Q exact, but is Q close means that is annihilated by Q. This is supersymmetry. All the terms in the Lagrangian are supersymmetric. But this guy here is not the Q of anything. So this is closed, but not exact. So the logic of localization is the following. You see the Yang-Mills term and the matter fields can have a coupling that can be sent to 0, and I can do a semi-classical approximation around small coupling, which means that I take the minima of this Lagrangian, the Lagrangian for Yang-Mills and Lagrangian for matter, and this will define the saddle point of my computation. So So the localization computation is quite involved, so I have no time to do all the details, so I'll give you the result. And the result in this case, and all the other cases that you find in the literature, is such that the full path integral localizes on a finite dimensional locus of saddle points. So the final result is of the form. The path integral on this manifold can be written as following. There is an integral, and we'll define the various object in the next few minutes. So there is an integral of a finite dimensional integral over a set of gauge variables. In general, this is the structure that you can find using localization, a finite dimensional integral. And then what may happen, and often happens, is that you can have to sum over various topological sectors. So your classical configuration, I'll show you this example in a moment, can involve a sum over topological sector, which means instantons, maybe this was the case in the original computation of Peston, monopoles, this will be my case, or magnetic fluxes on the spheres. So in general, this integral and this sum is what remains of the path integral. It just localizes on few configurations. Then you have an integrand, which is the value of the classical action times the one loop determinant. And here, just to make things precise, you have to divide by the order of the Weyl group. So let me tell you what are the ingredients one by one. First of all, the BPS configuration. The BPS configuration are essentially the saddle point. Let's call them saddle point. So essentially these are the minima of the action that I wrote before. And the result, and I'll explain why is that in a moment, is the following. So the minima of the action correspond to take a constant sigma. This is the scalar in the gauge multiplet. You can take a constant value of the gauge field along the time direction. And you have another equation that tells you that the curvature of the gauge field along the sphere, so I'm using Vierbein here that correspond, the E1, E2, and E3 correspond respectively to the sphere and the S1. And the curvature of the gauge field on the sphere is related to the auxiliary field D by this equation. So these are the minima of the action. It's convenient to complexify these two guys and write this combination. So the time component of the gauge field plus I, beta is just the radius of the circle, will play no big role in the following, and sigma is the scalar field.
E1, E2, and E3 are bases of coordinates?
Are Vierbein, shouldn't say Vierbein, is a frame on, in 3 dimensions. So, for example, you can choose E1 the theta, R the theta, E2 R cos theta, sin theta the phi, and E3 beta the t. Okay? What's the meaning of having this equation? This equation tells you that in general F12 is different from 0, which means the component of the curvature along the two spheres is different from 0. So if you integrate it on the two-sphere, you will get a non-zero result. This is a topological number, is essentially the magnetic flux along the two-sphere. If you normalize by 2 pi, you will get something which is different from 0. I call it M, and satisfies some quantization condition, because this is the magnetic charge on the sphere, and the quantization condition is essentially the following: acting on any representation of the gauge group, M, which lives in the algebra, exponentiated should give 1. More precisely, if you want to write in precise term, this defines the co-root lattice of your gauge group. More prosaically, because this is what is enough for us, for a U1 gauge field, M is just an integer, positive or negative. It's a magnetic charge on the sphere. And more generally, for UN, M just belongs to Z to the N. Okay? So these are a collection of integers. I haven't told you something. The saddle points, so these are gauge, these are commuting, mutually commuting gauge zero modes. Commuting means that the commutator of sigma with A and the curvature and in all possible combination is 0. So you have 3 guys that commute with a gauge transformation. You can always bring them in the Cartan subalgebra. So these guys, sigma, AT, and M, live in the Cartan of the gauge group. And as usual, since these are a joint field, with a gauge transformation, you can bring these guys in the Cartan subalgebra, but then there is a remaining of gauge transformation, which correspond to the Weil group of your theory. So more precisely, you divide by the Weil group. And another information about the set of saddle point is the following. You see what's the meaning of this sigma is the pattern of the gauge field. It has the effect of giving mass to the field, so it's a sort of real mass, dynamic or real mass. AT is the component of the gauge field along S1, so it's a Wilson line. So you know that Wilson lines are periodic, so the right gauge invariant object is the holonomy, which is the exponential of AT. So AT is periodic. And again, if you want to be precise, the right periodicity is the following. So AT is identified up to a 2 pi shift by a co-root element of an element of the co-root lattice. Again, more prosaically, for U1, AT is identified with AT plus 2 pi. Which means convenient to do the following. Instead of using the variable u, it's convenient to exponentiate it, since AT is periodic of period 2 pi. So in a sense, u live on a cylinder spanned by sigma. I think this is sigma equal plus infinity, sigma equal minus infinity, and x live in the, essentially in the punctured plane, C star. I will mostly use the variable x in the following. Now, where these guys come from? So these are the minima of the Lagrangians, but typically it's interesting to interpret them also as the BPS configuration. So these are the zeros of the variation of supersymmetry of the fermion. This is a general fact that applies to most of the localization computation. If you want to know what is the saddle point locus, you look at the fermion. Here it is variation, which I wrote in a bad way, I think. This is sorry, yes, the other one was correct. There was a sigma missing. And you look at the variation of lambda, and you set it to 0. So you see from this expression here that you get exactly what I wrote above. Essentially, sigma should be constant. There is no occurrence of the Wilson line. And these two terms, if you write explicitly the fermion as a two-component epsilon plus 0, you discover that this guy here and this should cancel simultaneously. So this is okay if sigma is in the Cartan subalgebra and is constant. And this other equation tells you that F12 is equal to D. Okay? So the equation that I wrote can be always, almost always, in all example of localization, extracted from the BPS condition on the fermion. You look at the variation of the fermion, you set it to 0. Now, so this is the so this is the variables U and M. What about the integrand? Now, the integrand is the value of the classical action times the one-loop determinant. So the difficult part of the story is this one, so I'm not giving the technical detail. When you have a problem of this kind, you hope that someone else has already done it. If not, you need to compute. You need to take a sphere, you need to take equation of motion for the fields, and you may understand what's the logic. You take all the fields, you have your classical configuration, you expand in harmonics on the sphere or whatever manifold you want, you evaluate determinants, and since you have supersymmetry, most of the bosonic and fermionic modes typically cancel in your ratio of determinants, and you're left with a finite part. This finite part is not easy to compute, so I'll give you the result here. Take it as a set of rules. Each different example of localization has different set of rules. In this case, what you discover is the following, that essentially the Yamis Lagrangian and the matter Lagrangian being exact give you 0. The only contribution to the classical action that you get is from the Chern-Simons term. And the Chern-Simons term contributes something of, if there is a Chern-Simons, only if there is a Chern-Simons you get a non-zero result. In terms of this variable x equal the exponential of u, you get a term like that. So you get this gauge variable, exponentiate with the Chern-Simons times the magnetic flux. The reason here is the following. In the Lagrangian, you have a term like that, K A wedge F. F on the sphere is essentially giving you the magnetic flux. This, if you evaluate these terms on the sphere, you put it AT here. AT is completed to I beta sigma by supersymmetry, and this is the term that you get. So this is the exponential of this guy, and become e to the u k m. So this term is easy to understand. Then you have the determinant. The determinant comes from the one-loop computation. And again, in all this business of localization, it's not really necessary to know the details of the Lagrangian, but you need to know the matter content. So how many vector multiplet you have, how many chiral multiplet you have. And in this case, the one-loop determinant give you for a vector multiplet, if the gauge group is G, you get a product over all the roots and you get an expression of this form. I want to write this as an integral, so let me put the measure of integration here. You are integrating over all the variable u. So what is this object? This object, x, essentially lives in the Cartan. U lives in the Cartan of your algebra. X, in a sense, lives in the Cartan of the group. And the expression product over all the roots of 1 minus x to the alpha is just what is known as the R measure. So this guy here is an invariant measure over your group, which makes sense. This is the contribution of the vector field. It tells you to take an average over the gauge group. The contribution of the matter field depends on the R charge of the matter field and is in general a rational function. So if you have a multiplet transforming in some representation of the gauge group, and you call all single components rho, so rho is the weight of the element in your representation, what you get is essentially a rational function of this form. Where R phi is the symmetry of your field. I'll give you in a moment an explicit example where you can see how you can explicitly construct the partition function for a field theory. So you see that this is a rational function in X. So the important point is that is the following. Here, I haven't written any superpotential. I can. I'm not writing explicitly the supersymmetric version. It's similar to the flat space one. The point that even the superpotential term that you can write in the matter part of the action is the Q of something. So again, the superpotential is irrelevant in all this localization business. You can put a superpotential. The only important point is if it is there or not. But the specific form is irrelevant. Finally, yes? So when you have an n equal 1 theory in 4D or n equal to 2 in 3D, you can add a superpotential. So these are interaction between fields. And you may think that this is the most important part of the story in defining your Lagrangian. Well, it turns out that the part of the Lagrangian which corresponds to the superpotential is the Q of something. So you can modify as you like. So you can turn it off. The superpotential is, in the example that I'll show you, not today, because there is no superpotential there, but at the end of the story for the black hole, there will be a superpotential, and I'll tell you precisely what implies in the computation. It tells you something. It fixes the charges of your fields, but no more than that. Okay? So again, that's why I'm saying that you don't need exactly to know all the specific details of your Lagrangian. If you know the matter content, you can write explicitly the matrix model corresponding to your theory. Now, then the last piece of the story is the complicated one. I'm not entering in many details here, but you also need to prescribe a contour of integration. Okay? So in this game, this function here has several poles. This is a contour integral in the plane u or x that surrounds part of the poles with a specific rules. The specific rules is dictated by supersymmetry. You may ask how supersymmetry choose for you the contour. Well, it's a long story, and it's the technical part that makes this computation difficult. And I can briefly summarize the logic. And the logic is that you could have already complained, since if I say here that I want to do a contour integral in the complex plane, you may say, okay, your BPS configurations depends on sigma, at. You complexify it, but the manifold of classical solution depends on 2 real parameters, so it would be more natural and correct to do the following computation. Sum over all magnetic fluxes, integrate over the U and the U bar, the classical part of the Lagrangian, times the ratio of determinant. And indeed, this is what you have to do to start your computation. Then you discover that for this particular model, there are also fermionic zero modes. So around the classical configuration, some of the fermions are zero modes. So that the path integral, if you do in this way, is 0. But then you remember that in the Lagrangian you have extra couplings. This one. So even if lambda and psi have zero modes around the classical configuration, they appear some way in the Lagrangian. So you expand your matter Lagrangian, you keep the zero modes down, you integrate over the zero modes, and the result is that you have to modify slightly this computation, and here you get an extra determinant for the zero modes. Well, it turns out that by supersymmetry, this integrand here is the debar of something. So that you can take your 2-dimensional integral and reduce to a 1-dimensional one. You also discover that since you have many singularities in the one-loop determinant, there are many singular points in the plane U of this expression. So what you actually do to do this computation is the following, sort of regularization. You first remove an epsilon neighborhood of everything. You regularize your theory in such a way that everything is finite. You apply this trick. You transform the integral over an integral over this boundary. So you get an integral over the poles of the integrand, and then you send epsilon to 0. When doing this, if you do things correctly, some of the guy goes to 0, and the other instead are non-zero and are computing the poles of this integrand. So the final result is the following, is curious, but is the result prescribed by supersymmetry. You need to take a contour that surrounds some of the poles of this integral, and which one? Essentially, and I'll show you the example now, so that the way it works it will be clear. You take the poles of the fields with positive charge. Only. This is the rule. Comes from supersymmetry, and I have no time to explain it, it's quite technical, can be written in a nice geometrical language in terms of the so-called Jeffrey-Kirwan residue, which has appeared many times in the localization business in the last few years. I will not discuss this. If you want, you can ask, but because I prefer to give you an example of how you compute something with this, what I want to do.
So Alberto, before you erase this Lagrangian,
yes.
So the Lagrangian depends on the choice of R charge R phi. Is this a free parameter? Is there a one-dimensional family of supersymmetric theories on this 2 closest one?
Yes. Thank you for asking me that, because yes, I was forgetting to tell you something important. Yes, their charges are not fixed, and you can have more than one, so you need to make a choice of that. So you can have families of Lagrangian depending on their charge that you choose for your fields. Indeed, what happens is that if you apply the formula that I gave you now, what you compute for a generic field theory is a number, 5, 10, 25. It's a pretty boring object. So the things are interesting only when you have flavor symmetries. If you have flavor symmetries, you can choose a reference arc charge and say that any other arc charge is a combination of an arc charge and a flavor symmetry. If you have a flavor symmetries, what you can do is the following. So you can couple your Lagrangian to a background multiplet for the flavor symmetry. So if you have a global symmetry of your theory, you can, if you want, weakly gauge. And then you can turn on some background for these guys. This background will preserve supersymmetry if with the same trick that we used 1 hour ago, the variation of the fermion is 0. So essentially you can turn on a non-zero value for this guy, and for this guy, provided that this guy here is arbitrary constant, this guy here is a generic constant, and the curvature of this field is equal to the D term. So again, what you can do is that if you have a flavor symmetry, you can turn on a Wilson line for the flavor symmetry. You can turn on sigma f, which is essentially a real mass for your theory. And you can turn on a magnetic background for the flavor symmetry. Essentially what happens is the following. Whenever you have your Lagrangian, if you have a covariant derivative here for a field, now this is replaced by a covariant derivative of the fields times some background for some gauge field, which is a background field, which is a magnetic field here. So essentially you can put your theory in a magnetic background for all the flavor symmetry that you have. What changed in the previous computation is the following. These guys here can be combined to give a complex guy that I call UF, that you can exponentiate. As before, and this appears as a background, so it's not a dynamical object, but for all flavor symmetry, you can have a term like that. This means that in the previous expression, you can essentially replace every x to the rho here with an x to the rho times some new xf, which is a background flavor for the flavor symmetry. So to make this concrete, let me write the matrix model for the simplest theory that comes to my mind. The simplest theory that comes to my mind is super QAD. Super QAD is a U1 theory, gauge field U1, with an electron Q, a chiral field, and anti-electron Q tilde that are also represented as a chiral field. So this guy, Q and Q tilde, are two chiral fields. They transform with opposite charge under the gauge group. Let me call it capital G, the gauge group. Okay? Then you have other symmetries. There is a axial symmetry, that flavor symmetry, that rotates the two guys with the same charge. There is no superpotential. This is plain super QAD, okay? No superpotential in the game. So if I rotate with the same charge Q and Q tilde, this is a symmetry of your Lagrangian. Then there is certainly an R symmetry, and I can choose whatever R symmetry I like. There is no superpotential. So for example, I decide to give charge 1 and 1 to Q and Q tilde. Notice that these two symmetries are different. This is a flavor symmetry, so boson and fermion in the multiplets transform with the same charge plus 1. This is an R symmetry, so if the boson transforms with charge 1, the fermion transforms with charge 0. And in addition to this, just to make things complete, there is another symmetry that always appears in 3 dimensions, which is called the topological symmetry. And the reason for which there is such symmetry is the following. If you take a U1 gauge field, you take its curvature, and you take an epsilon of it, because of Bianchi identity, this is automatically a conserved current. So in 3 dimensions, if you have a gauge field, you automatically have a U1 gauge field, you automatically have a symmetry associated to it, which is constructed with the dual curvature. Okay? So what happens about this symmetry? Typically, this is a topological symmetry because there are no, the fields in the Lagrangian have no charge. The objects that are charged under this symmetry are more exotic, are the so-called monopoles that can be constructed by essentially dualizing the gauge field along the moduli space to a scalar and construct objects that semi-classically are of the form sigma plus minus I gamma. These are monopoles. So only non-perturbative objects are charged under the topological symmetry. Let me write you the partition function in this particular case and briefly evaluate it. So what time is it? 5 minutes. So I don't know if I can make it today. So maybe it's time to stop it now and I finish with this example. Next time, tell you.
Since you started writing it, if you, in 10 minutes?
10 minutes. 10 minutes, okay? Okay. So this is the form of the partition function for super QAD. Let me explain you the various building blocks. Once you have done all the localization business, the computation of partition function is a sort of game. You have a matrix model, you need to know the rules, put for each field a particular contribution, and this is the contribution of Q. Maybe I can slightly overlap the two blackboard. The contribution of a chiral field is of this form, is a rational function. Okay? So at exponent there is the arc charge, the magnetic field, and then a rational function. Oops, I cannot really superpose because I need the charges, so let me go back. So this is constructed in this way. X is the gauge variable, is the remaining of the gauge field in the path integral, lives in the Cartan, and appears in this combination. There is always square root of x, 1 minus x. And the guy Q has charge 1, so I put x here, y minus x there. This is Q tilde. the difference, y minus x, 1 over x that appear here, is due to the charge. The charge of q tilde is -1. So I put an x to the -1. Okay? So these are just the charges. Then I put an extra parameter y, which is a background parameter. The result will be a function of n, of y, and n. Y is associated to this flavor symmetry. It gives the same charge to q and q tilde, so you see that I put a y here and a y here. Okay? The power reflects the charge. Then there is an exponent. Essentially, if I choose r charge 1, is my choice for all the fields. This is -1, and this cancels the other one. So there is only the magnetic flux. The magnetic flux I split in two components. There is a gauge component. I'm integrating over it. So there is in the path integral a sum over all the possible topological sector. M is a gauge variable. I'm integrating over it. And it appears at exponent here with sign plus and sign minus here because the charge is opposite. And then, since I have a flavor symmetry, I can put a background flavor symmetry, background magnetic flux, and this is the n, which appear in the final partition function. And you see that I put plus and plus because the charge is the same. So y and n are backgrounds, x and m are integrated over, and this guy, I have no time to explain all the details, but is essentially a magnetic flux and a background gauge variable for the topological symmetry. You can show that they enter in this particular way. So if you have to evaluate this, you need to know what is the contour of integration. And the contour of integration is this funny Jeffrey-Kirwan residue that in this case tells you take the poles of positively charged fields. The charge with positive charge, the field with positive charge is the Q, and the Q gives this contribution. So essentially I need to take all the poles that come from this expression. Now, how can I do this computation? Well, I can do the computation for each finite m, or do a trick. So since I need all the poles of this guy, and m goes from -infinity to +infinity, I see that I have poles whenever m is greater or equal to -n plus 1. Okay? So there is a lower bound, and then all the other terms bring poles. So what I can do is the following. I forget the m, which are very negative because they give 0 to my integral, and for the other, I use the geometric series. So I can take a very large cutoff, for example, say I choose m much bigger than some minus capital M is positive, so that if I resum all these guys, I take all the contribution that give poles. Then I can write this expression as follows. There is a sum over m. If I put together all the terms with m, these are and then there is another term which is okay? And then here I want to sum from a large negative cutoff to infinity. Let me call this expression with a name, e to the IB. And this expression is what remains of the path integral when I set m equal to 0. Okay? I call it the integrand at m equal to 0. If I now resum If I now resum, I get the following. The x over 2 pi ix. There is this part that is untouched by the resummation. There is a term which comes from my cutoff, and obviously at the denominator I get this expression. So that the sums disappear, and I still have to do a contour integral. What happened is that the poles that I was interested in, all of them, in a sense, are moved to the denominator of this expression, so that I can write the following formula. I perform the residue theorem here, and the residue theorem here tells me tells me take the derivative of this guy, so it's a simple pole, and evaluate the rest in the solutions of this equation. Okay? There can be one or more. So this is the result. If you write explicitly what is this function e to the ib, you discover that the equation that you need to solve is this one. And I'm finished. In this case, luckily enough, you can solve it for x, and you find that x star is equal to 1 minus zeta y minus zeta. You plug it here, you do a little bit of algebra, and you find the following result. So you look at it and you say, okay, it's a rational function. That's the general result that you get with this game. So what is good for this computation for field theory? I'll show you what is good for black holes in the next lecture. For field theory, let me notice the following. This is written in this way, but I can also write it as following. As a product of three guys. Okay? The product of three guys that looks like, each of these looks like the building block for a chiral field in my integrand. So if I have a free theory and I have to compute the partition function, and just put the building block for the chiral field one near to the other, and I get the result. And indeed, this theory looks like a theory where you have three chiral fields, some flavor symmetries, and indeed, it is known, is one of the first examples in mirror symmetry for n equal to 2 theory in 3 dimensions, that super QED has a dual. This dual is the so-called XYZ model. It contains three chiral fields, X, Y, and Z, with a superpotential. So it's just a free not free theory, but a theory without gauge field, three chiral field, and a superpotential. The superpotential here just tells you that there are some flavor symmetries. If you do the exercise of computing the flavor symmetries for this theory, you will discover that there are two of them. You can assign charges to the field in such a way that you precisely reconstruct this expression. So indeed, typically, as I told you before, one of the applications of localization is the following. You have dual pairs, you want to check, you want to propose your own new duality. Well, you need to evaluate the partition function for the dual theory. You will get complicated expression, in this case a rational expression that depends on this parameter y and zeta, and also depend on the arbitrary magnetic charges for the flavor symmetry, but is rational. You can evaluate for the dual pair, and you have to check that these coincide. The physical meaning of this parameter, I have no time today to explain it, so I will discuss in detail in the context of the black hole, because these are important. For the moment, these are just parameters for all the possible flavor theory in your game. Okay, so I stop it here. I'm out of my time.
So let's thank Alberto for the very nice lecture. Okay, so we'll have time later this afternoon for a more extended discussion, but if there are a couple of urgent questions, please feel free to ask them now.
Is a mass term or is a massive field massless?
No, the original one, no, massless.
But in principle, you can add a mass term.
You can add a mass term, but yeah. This y here, in a sense, is a... so you can add two types of mass term. A real mass, because you are in 3 dimensions, a real mass or a complex mass. If you add a complex mass, what happens is that you have a superpotential, and as I answered before, the superpotential is irrelevant, but what you lose is see if still there, you lose one symmetry. Clearly, if you add the term Q tilde, assigning charge 1 to the guy breaks that. So what you do is the following. If you want to compute the partition function for the massive QED, you do the same computation, the superpotential is irrelevant, but you need to turn off all the parameters that correspond to this flavor symmetry. So you set y equal to 1, and you kill n. So essentially, you take the same expression that I gave you, and you put y equal 1, and n equal to 0. That's the things that you do. So superpotential in this game always do this kind of thing. Fix the charges and the global symmetry of your theory, but they do not affect in a big way the partition function.
So what about the assignment of arch charge? You chose 1, 1, but you would have chosen any...
Yes, because if you have no mass, you can mix these two guys in the way that you like. Essentially, you see here that there is an arbitrary parameter. This n you can see as a background for the flavor symmetries. Or if you want, if you decide that your symmetry is a combination of these two, it becomes a background for this R symmetry. Okay? So there is a family of possible theories that you can construct using the freedom of combining R symmetry with flavor symmetries.
Okay, I don't see any further questions, so let's thank Alberto again. So we'll resume at 2:30 with lectures by Johanna and Menger. And so for now, we can have lunch at the cafeteria downstairs. I think most of you know where that is. Otherwise, you just follow the flow. And you can pay with either euros or Swiss francs at the cashier.